Good morning, everyone. So my name is Narayan Desai. This is Brent Bryan. We're SREs at Google. We've spent the last few years working on analytics products. And so this talk describes work that we've done over the course of about the last 2 years. So we're really excited to be able to present it publicly. So I wanted to actually start with some acknowledgments. This isn't just our work. We have a larger team, including Jeff, who gave a talk yesterday in the audience. We've worked with a bunch of partners across a variety of other service teams at Google. And we've really benefited a ton from sponsorship and advice from a number of folks that I listed there on the bottom line of this slide. You know, I think the real point that I'm putting this up at the front of the talk is because you don't get anything done alone, right? Anything hard requires a lot of people to contribute in a variety of different ways. And if we're going to solve the reliability problems that we have in front of us, that's what we need to do, fundamentally. And with that, let's start with the talk. So this work all started with one really simple question. To set the stage, I've been at Google about 5.5 years. So at that point, I had been at Google a couple of months. I was responsible for one of our analytics services. And I asked myself one question. Is it working? Now, I wonder how many people in this room feel like you can answer this question about your services? Like if the service is really working. Is anybody confidently raising their hand? I don't see anybody confidently raising their hand. Everybody's OK, one confident person at the back. We see a lot of people. Oh, two? OK, this is exciting. I'd like to talk to you after. I see a lot of people looking real nervous. Right, just moving their hands like this, saying, sort of, right, a little bit, like. So I had the same realization. What I realized is that for the service that I was responsible for, I could tell if it was on fire. I could tell that it was doing something. And I could tell that certain aspects of the service were working and it looked busy. But that's not really what our customers care about, fundamentally, right? Like they care that the service is working. And this really started a lot of, nervous thinking. Like, this is the problem that we need to solve, right? So we're SREs. We should all be able to answer the question, is it working? Like, if our management shows up at the door and they say, is the service working? We should be able to say yes or no with some amount of confidence. And I don't think that we can do that today, right? We can talk about certain aspects of the system, but that's not comprehensive. And I think this really prompted us to sort of go back to basics and really try to think deeply about what we were doing. So let's talk about reliability for a minute, right? I think one of the problems that we have is that our field doesn't actually have solid terminology. So when you use terms of art, people may mean different things. If we all talk about reliability, we may be talking about completely different things. So for the purposes of this talk, this is our definition of reliability. We think that the three critical components of it come down to availability, performance, and correctness, right? Effectively, is the service available? Is it doing the thing it does, efficiently at sort of the normal speed that it does? And is it doing what you expect it to do in terms of producing correct results, right? Now you'll notice as I describe this, I used mushy language for all of this, right? Because this is all kind of subjective. There's some of you might know Hiram's law that customers grow to depend on the behavior of your system even if it's not specified. And so if you work around bugs, you may break someone's code. We've all seen this where someone depends on some unexpected behavior, right? Correctness is actually the hardest of these topics. And I'm not going to talk about it very much today. But I would argue that all three of these characteristics have that same basic situation where there's a lot of ambiguity in terms of what availability means, in terms of what performance means. And I think if we're going to make real progress on reliability, we need to get a whole lot more specific and focused and fundamentally quantitative about it if we're going to be able to really tackle these problems. OK, so we've all started here. I've been in the field about 25 years at this point. The way that this all started was you stand up a service. You're like, OK, if there's a problem, just page me. So you start adding alerts, right? And then as you get paged, You're like, oh, OK, that wasn't actually a problem, so I'm going to tune the alert. And then you get paged again, and you're just sort of like mutating the system to try to figure out what's going on. And this isn't very satisfying, and it's certainly not principled in any way. But you're just sort of trying to survive, right? Like, nobody likes getting paged to death, and we have all dealt with pager storms, right? So this is where we started, right? Now, fundamentally, SLOs are, I would argue, the core process of SREs, right? If you've ever been to an SREcon or consumed any of the SRE materials out there, you know that SLOs are the solution to your problem, right? So they take this paging problem and they make it all much easier, right? So the problem is that we've overloaded SLOs to solve all of our problems. And I'm not going to talk through each of these, but really what you're talking about is whenever we have a problem, the answer is now SLOs. So you end up with SLOs to solve each of these problems. You end up with SLOs that are misapplied because they were designed for one of these problems and they're used to solve a different problem, right? So to give you a really concrete example, SLOs are often used by service teams to understand the goals that they're setting for a service, where SLOs are often used by the consumers of a service to understand what performance they should expect, at least at the worst case. Now, these are very different problems, and they'll have very different solutions. And if you're using the same SLO to try to characterize a system in both of these dimensions, it's not going to work, right? And so we've ended up in this situation where we have started over-relying on SLOs, right? And so fundamentally, these feel like one of those as seen on TV type things. We're like, OK, so you had this problem, and SLOs are the answer, right? This is the Vegematic of the SRE world. And it's not satisfying. And I think that anybody that has rolled these things out for any complicated service knows it just doesn't really fully work. Like, yes, it works sort of sometimes, but it's complicated and like it doesn't work a lot of the time, and I don't entirely know why. And clearly the answer, well, right. So let's think about how this looks for a really simple service, right? This is just like a Postgres instance. Something very simple. The user sends some SQL, they get back some data. You're like, OK, I'm gonna define some SLOs. I'll have some availability and performance SLOs, and I'll do some stuff for correctness. So I'll think about looking at the numbers of errors that I'm returning on my API as an availability SLO, and I'll set like a P99 or a P99.99 latency SLO, and I'll have some probers running to make sure that the database always has traffic and it's answering some queries, and like this will be great, right? So it turns out not so much, right? You look at availability, and it turns out that this is a whole lot more complicated. So for example, it's very easy to misclassify the errors that you have. So for example, if there's a proxy in front of your database and it does any sort of modification of queries as it passes them through, you might misrecognize a malformed request as being the result of user behavior as opposed to something that the system is doing that you should fix, right? And so counting these availability events is actually pretty tricky. You also have issues with deadlines, where if deadlines are set improperly, maybe the underlying service is still working, but the client didn't wait around long enough to get the response. Or the greatest of these is if you have clients that retry, which, admit it, we all do, when there are problems, the first thing they're going to try to do is retry, right? And so if you have a small problem, often it ends up looking like a big problem because you have a customer that's doing something that's not working, and they try harder and harder to not do it, or to do it again and again. Well, to not do it eventually is what ends up happening, right? But so from the perspective of this availability SLO, this is actually a really noisy signal, and it's really hard to interpret what's actually happening. Now, turns out that's the good one. Performance is even worse. So if you have a database with arbitrary SQL being submitted by customers, what should the P99 SLO be? I mean, I don't know. Nobody can tell you, right? Because it's going to completely vary based on the workload that's submitted to the service. It'll change over time, right? If you have diurnal patterns in your service, maybe the workload is different overnight versus what it is during the day. So your P99 is going to move. And so it's going to be impossible to interpret what's going on. And I think the other problem here that you end up having is that probers are narrow, and they're often simple. And that means that they exercise a small part of the surface of the service. And as you're analyzing the performance of the probers, you know that the narrow code paths that they're exercising work, but you don't really know what's happening in the rest, of the service, right? So again, on the correctness side, it's hard. It's really hard, and everyone works really hard on testing, and there are systematic approaches for this, but I don't think we have a deep theory of this yet, and I think we need one. And so if anybody's looking for interesting problems to tackle, I think this is a great one. Okay, so that didn't work. So how does this all play out? Well, we duct tape, right? So we have a really long history of using SLOs to try to answer reliability questions at Google, and we have started adding things on, right? So the most common thing that you see is you're reading a postmortem, and one of the things in the postmortem is, oh, we were missing an SLO. We need another SLO here. So you keep adding SLOs, right? And sometimes the aggregation is a problem, and so you maybe set up customer-specific SLOs, or perhaps you tier your SLOs, or you attach your SLOs to CUJs, or you parameterize your SLOs, right? So once you parameterize your SLOs, you end up in this really funny space. So this is actually true. One service at Google that has 250,000 SLOs. Now, when you have that many SLOs, what do you do with it? Nobody knows, right? Like, it's a huge problem, right? So fundamentally, as you go through this, the answer is always, more SLOs, right? And your prize for this, it's a pie eating contest, right? Where the prize is more pie. Every time you have a problem, you get to work on SLOs some more, right? And it's this never-ending battle. And for the record, that's not Brent.
No, not me.
He doesn't do pie eating contests. And by the time you consider, right? I'm not saying that we've done this, but certainly people have talked about it. If you have so many SLOs that you're thinking about setting an SLO, talking about how many of those SLOs can conform or need to conform at any given point in time, you really need to step back and look at what you're doing, right? This is bonkers. So we've been struggling making SLOs work for high fidelity use cases for a long time, and it just hasn't worked really well, right? SLOs can see catastrophic failure, they can see certain sorts of problems, but it's not a really universal solution. And so we really started to analyze this, and we figured out why. So fundamentally, the idea of SLOs are based on, you could call them errors, you could call them good or bad events, but the key concept of SLOs is that for every event, you can classify that event as a good one or a bad one, right? A failed request or a successful request, a request that was fast enough or a request that was not fast enough. And then what you do roughly is you calculate a proportion. You look at all of the bad ones over the total number of events that you have, and you look at that percentage, and you end up with hopefully something above some number of nines, but you end up with a percentage. Now, what's the problem with this? Well, fundamentally, errors are shallow data. So as our friends in the qualitative reliability space would say, this is bad data, right? The problem is that errors, particularly counts of errors, can't capture the richness of the problems that happen. And I love this Tolstoy quote. It really captures the thing, right? Like, this is the same way that every outage is different, right? If you have 10 errors, those 10 errors aren't necessarily comparable. You shouldn't necessarily weight them evenly. There are a whole bunch of problems here, right? So requiring recognized errors is the key to this SLO approach. And this is ambiguous, right? Fundamentally, this, to borrow another term from the qualitative folks, this is a social construction, right? Like, the errors are just things that we have agreed are errors. There is no Platonic ideal of an error. When your code emits an error, that's because you've decided that if these three conditions match, that is an error. And if it doesn't, then that request was successful, right? That doesn't mean that in some deep sense that errored out request was an error or the successful one was some deeply successful thing, right? This is just a convention that we use to classify things that have happened. And these classifications can go badly awry. So to give an example from a very, very long time ago when network offload was a new thing, I remember debugging a problem on an IRIX system 20 years ago where the problem was that the NIC firmware was corrupting the data but passing along good packet checksums, right? And so these were being passed through. Everything looked cool, but the upper layer of the application saw this garbled data, and we needed to figure out what was going on. And it was a real pain to diagnose because, on the network layer, everything looked good. There were no packet corruptions that were being detected. Everything was fine. But it turns out that this process of categorizing errors and recognizing errors is really problematic. And so you can end up with undercounting, particularly. So calibration errors are a huge problem. So when you think about errors that you're recognizing as a result of setting a performance threshold, you say, for example, 99.9% of my requests need to happen in under 25 milliseconds. Now imagine so again, you now have an SLO, and you're using it for all of those purposes on the earlier slide, right? Now imagine that your vendor comes in, and your VM gets migrated over to a faster storage system or a newer generation of hardware, and it's now much faster. And so the true calibrated version of where P99.9 should be that you should be alerting at has dropped from 25 milliseconds to 15 milliseconds. What happens? At this point, whenever you actually see an alert, everything has been on fire for a very, very long time. And the legitimate situations that you should have been alerting in, you don't see because performance looks good, you haven't recalibrated. And so the problem here is that we don't have a maintenance cycle. Like, we don't know how to think about calibrating these systems, right? There's some instruments that get calibrated on a regular basis because it's important to do. We don't have this life cycle for SLOs or thresholds. And the alerting life cycle is, it's paging us too much, let's make it stop. Right? Or it's paging us not enough, make it start. Right? It's not fine-grained and it's not proactive. So this gives us really, really terrible data products. And we see this, whenever you try to use SLOs to locate subtle phenomena, subtle reliability phenomena in a system, you just can't see anything. Right? Many of us have dumped the data into a data warehouse and try to do complicated analytics, and it just doesn't work, right? And I think this is fundamentally why. We have tricked ourselves into believing that errors are the currency of reliability, and that's the way that we can understand our systems. But fundamentally, we just can't, because by the time you get the data into this form, what you've done is you've taken a very, very rich signal that is high dimensional and contains lots of data, and you've flattened it down to a timestamp and a Boolean, right? This is very, very lossy compression. And I think this has actually caused a whole lot of folks in our field to decide that quantitative analysis is impossible. I think that's actually wrong. But when you have data products like this, it's easy to understand why. You look at it, can't see anything, you're like, OK, we just don't know how to do it. We don't understand what the service should be doing. So we're in trouble. OK. So, what now? I started this with the question, is it working? This is still important. I would imagine for everyone in this room, you have people for whom you are responsible to make sure that services are working. It is really critical that we be able to do this, and we need to be able to do it reliably and robustly and confidently, right? And we can't. And I think this is really where we part ways with the qualitative folks. Qualitative methods are important, but I think it's important that we have a robust set of quantitative approaches as well, because at the end of the day, when your service is having an outage, that's not a social construct, right? You and your customers are in an objective reality where things are not working and it is causing business impact, right? When I'm at home and our power provider has an outage, the lights go off, and we can all agree that the service is not being delivered, and that started at a particular time and it ended at a particular time. Now, our services are a little bit higher dimensional than is the power system delivering power, because we have a lot more resource types and the interdependencies are more complicated in certain ways and so forth. But fundamentally, we need to take a quantitative approach because there is an objective reality and we need to be able to analyze it. So at this point, I'm going to hand the mic over to Brent to talk about our method.
All right. So as Narayan mentioned, SLOs don't seem to be working here for us. So what are we going to do? This is where we take a deep breath and start looking at performance analytics. So let's take a step back. Let's look at our example service again. So again, we have a consumer making some requests to Postgres. And what is it that this consumer is actually interested in? Well, as a customer, as a consumer, they really care about, is this service working in the way that they expect it to be working? And where does those expectations come from? Well, they could come from the documentation. They could come from the SLOs or the SLAs that we've put on that service. But most likely, they're going to come from the experience of that customer using that service day in and day out. And they'll have a pretty good idea of how the service should be working, even if it's not the way that you think it should be working. As a customer, as a service provider, we have the same question. Is it working or not, right? And together, across both the customer and the service provider, we want to know if it's broken, or when it's broken, unfortunately, is it you or is it me? And this is not meant to be a blame casting exercise, but it's really meant to be a collaborative exercise where as a service has an outage, both the service provider and the customer want the service just to be restored. So what we need to be able to do is figure out where that problem lies and dig into that and be able to root cause it. And being able to understand across this boundary of whether it's on the customer side or on the service side is really helpful so that either side is not wasting time digging into their service or their client when in fact they should be helping the other person on their side of the boundary. So how are we going to think about this? So let's look at this from the service provider's point of view first. So what do they see when they look at this simple service? So what they're going to see is they're going to see workload performance, but they're going to see it across all of the customers, right? There's not, I mean, we could tag and put some census data on this, but in general, what we're going to see is we're going to see all this aggregate data across all these different customers. And this is going to be complicated by the fact that there's a lot of different factors that are going to go together to combine together to make to result in what performance is actually observed. So it could be that there's mixed shifts in the workloads. Maybe the workloads are shifting over time, or the proportion of them is changing. Could be things like the environment, like what connection's being used. Or it could be just what type of query the customer is putting into the service, right? So is it a dev query? Is it a QA? Is it actually a prod query? Is it something that customers actually care about? Or is this just a quick one-off type of thing? Think of your select star from table limit 10, which you probably get a ton of. So when we look at what the service providers see in terms of performance, because of all these complications, we're going to get data that looks like this. It's probably a little hard to see in this plot, but this is a log plot on the y-axis. And you can see that the latencies here for our queries are going to span something like 6 orders of magnitude, right? So Narayan was asking earlier, how long does a SQL query take on a database engine? And the answer is, depends. I don't know. Less than 8 hours. I don't know if that's helpful for anybody. So that's probably going to make you feel a lot like this. All right, let's pivot. What do the customers see? Right? So we might not know the performance of our workloads, but our customers actually have a pretty good expectation of what they should be seeing. Now, why is that? Well, think about the workloads that our customers are sending into these services. So here's an example query. This customer might be sending in a query. It might not be exactly the same query every day, but it's going to be a query that looks a lot like this every day. In general, the data set's going to be changing only moderately. It's probably only growing slightly day over day. The types of queries that you're going to be getting, whether it's going to be a 4-star rating or a 3-star rating, these types of things probably change pretty gradually over time. So as a result, when the customer runs this query, they're going to have a good expectation of what the performance should look like, right? And it's going to look something like this, right? So instead of having 6 orders of magnitude difference in performance, it's going to have a much, much narrower band of expected performance. So what we see And what we expect is that services should be consistent over time. Now, consistency is an interesting relative measure, right? It's not a statement of the service should be performing well. There's no definition of well, to be clear. It's just that the services should behave today the same way that they did yesterday and the day before. And if we can maintain that contract, we believe that our customers will be happy. So let's think through a high-level model of how this is going to work. We have a customer with a workload. We have a service provider with a service. And the customer is going to come with this workload, which has a specific intent. And for instance, the query or the code, or they want to get back the cute dogs that all of their friends like. And we want to then run that workload on our service and see how it performs, right? So we're going to take this workload, we're going to put it on the service, we'll observe some performance, and then from that performance, we want to be able to derive the reliability of the service, both for the service provider's point of view, but also for the customer. So both sides of this equation want to be able to look at this performance and figure out and answer their own reliability questions. Is it working for me? Okay, so let's take this model and expand it a little bit. So what do each side of this equation see? So on the customer side of the equation, clearly you have the workload, for instance, the query. You have the intent of what you're trying to do. Is this a prod query? Is this a dev query? Is this just some analysis or batch job that I'm running in the background? So I understand what the requirements are, what my expectations are in terms of, for instance, latency or reliability. I know I have a good sense of what correctness means. Typically, when I run a query, for instance, for cute dogs with 5 stars, I get the results back, and I can validate that those results actually make sense for the query that I just made. I have my own set of logs, right? And I actually have the source code for the query that I made, for instance, the SQL query. On the other side, on the service provider side, right, they have their own view of the world. They understand the service architecture of where this query ran. They understand, exactly what the infrastructure looks like, what the environment is, where was this sharded, what was the database look like. Likely there's a whole bunch of dependencies and a dependency graph that's involved here that you have to think through and think about, how the dependencies are falling apart, if they are. We have our own internal metrics and logs, and of course, there's the source code on the service side as well. Now, look at what's shared. Very little. So in the cloud dashboards, you'll have some shared logs and metrics. And that's basically what we have as a key right now to piece together what the client sees or what the customer sees and what the service provider sees. And so as a result, we have no consensus elephant, right? This to me is, we've been talking and we've been hearing about observability quite a bit the last couple of days, and this to me is an observability problem. We cannot observe across both sides of this spectrum. And this reminds me a lot of the parable of the blind folks looking or touching an elephant, right? So if you touch the ear of an elephant, you might think it looks like a fan. If you touch the leg of the elephant, you might think it looks like a tree trunk. If you look at the trunk of the elephant, you might think it's a snake. And it's not until you've kind of seen both sides or all sides of this elephant that you're able to piece it together and understand how this thing aggregates together to make this bigger, broader creature. So as I said, what we need here is this end-to-end information passing, all the way from the intent on the customer side to the service behavior on the service provider side. So let's go back to our model and think about how this looks. So again, here's our service provider providing some service. We have a sense of what that performance looks like. Again, it's about 6 orders of magnitude because how long does a SQL query take? But as soon as the customer shows up with a workload, now that workload has an intent. That workload is specific, right? There's a specific query that they're trying to run and over a specific set of data. And they have a sense that with that intent, we now have a good sense of what that performance should be, right? we all know what that performance should be. That performance should be exactly what it was yesterday, right? And so because we know that, when we go through and we combine these two data sets, we can actually see this on both sides now. And so now we have a good sense of what the reliability should be on both sides. Now this, of course, is one customer. What the service really wants to be able to do is do this for lots of customers. And so when you do that, each customer, of course, has different intents. They have different workloads that they're running in different environments, and each of those is going to have their own different performance, right? But what's going to happen is each of those are going to cluster, and they're going to cluster in a slightly different area in the performance space. Great. That's it. It's just that easy. We're all done. All we got to do is figure out what people's intents are. We've already got the data on the performance side. On our server side, at least we can grab that. Just split it out, and we're done, right? So this is just the summary three-step solution to do this. All we just need to do is partition the workloads by intent, like I said. We can just analyze the performance, and boom, we're in the money. So no problem, right? Everybody's got this? We can do this? So what I want to talk about next is a technique that we've been developing for actually implementing this in a statistically rigorous framework. So the technique that we have is called 2 sigma. The name will become a little bit more obvious as we run through here. And so the goal here of the 2 sigma technique is to really leverage this idea that workloads with the same intent should have self-similar performance day over day, right? So like, if a workload looks the same as it did yesterday, it should have the same performance on the service day over day, unless something changes, right? Like unless the workload changes or unless the environment changes. And if either of those changes, then you'll see a change in performance, right? And so a change in performance is an indicator that something has changed on either side, right? And so given that hypothesis, what we can do is we can take our workloads and we can partition them into cohorts. Now, a cohort is effectively just what we call a cluster, right? And the idea here of these cohorts is to approximate the intent, right? So intent might be a specific query for a specific customer. It could be shared across customers. Each intent is kind of independent and depends exactly on the implementation and the data sets that you have. So really what we're trying to do is we're trying to grab together those intents that have this self-similar performance and use that as a way to figure out to derive the expected performance from historical data. So that's what we do in the second step is that we're going to go through and we're going to build these performance baselines, right? So basically we're going to look at all the data from the past 30 days, and we can build up distributions, and parameterized. We can approximate them with a parameterized form, like a normal distribution or some other distribution. And then given those distributions of baselines, when we see new events, we can compare the distributions that we've created in the baselines with these new observations and effectively compute likelihood scores, right? So at a high level, what you should think about this is a hypothesis test where the hypothesis is performance today is exactly the same as it was yesterday, right? That's the null hypothesis. That's the hypothesis we either want to accept or reject. So as a result of this, what we're getting is this set of events with predicted likelihoods. And this then we can use as a time series. We can join them together, create a time series of these summary statistics. And then we can aggregate them and look for these extreme outliers. And whenever we see outliers, especially if they cross multiple of these intents, we can assert that there's an issue on the service side. If we only see it on one specific intent, it's probably more likely to be on the customer side, again, depending exactly on how the cohorts are constructed. So let's dig a little bit deeper into how we can create these cohorts and how we create these baselines. There's going to be a little bit of math here. If you've done statistics before, this is going to be, it's basically hypothesis testing with normal distributions. I'm going to try to go through it fairly slowly, but feel free to ask questions if I go too quickly. But what we're going to do is we're going to make a couple of quick approximations just to make the math work a little easier. So the first approximation we're going to make is that we're going to say our performance distributions follow a normal distribution. This is not true. Anybody who believes this? No, right? Like specifically, normal distributions can have negative values. If we could get performance with negative values, that would be awesome, but we can't. So this is not true. However, like I said, it makes the math work, and it turns out that it works most of the time. So like, go with me here. The second thing we're going to assume is that we can somehow model our errors, right? So there's going to be a bunch of distributions that don't fit normals particularly well, or they might not. Might be poorly specified with normal distributions. Let's assume that we have a mechanism for dealing with those right now. So we're either going to be able to fit them again with a normal distribution, or we'll just exclude them. And in practice, what we find is that excluding them tends to work pretty well. All right, cool. So if we assume if we make these two assumptions, then what happens is that as we get these new workloads in, and we want to compute the likelihood of each of these workloads, we can actually just compute z-scores, right? Z-scores are like a one-to-one proxy for likelihood. And it turns out the z-scores are super easy to compute, especially with normal distributions, right? Like, we're off to the races.
So for folks that aren't familiar with z-scores, basically a z-score is if you put a new event on this normal distribution, it's how many standard deviations it is from the mean.
Yeah.
Right. So it's a dispersion metric, and it's all sort of normalized across all of these distributions.
Yeah. So the cool thing about z-scores in particular is that now these likelihoods are all IID, and they're in the same space, right? So before we had all these different workloads with all these different intents, right? And each intent had different performance characteristics, right? So if you're doing your select star from table limit 10, you'd expect that to be pretty fast, because all you have to do is get 10 arbitrary random entries and return them. And if you're going to do a cross join with 15 tables, like, that's probably going to take a while. But now, by moving into this likelihood space, both of those queries are actually in the same normal space, right? And so all of our performance is IID, and it follows this normal distribution, right? Across all these different things. They're all normal distributions, which is really great because it turns out that adding normal distributions and doing math with normal distributions is super easy. It's also nice that computing normal distributions and z-scores and stuff like that is embarrassingly parallelizable. So it turns out that if you want to run over logs, for instance, and do this, MapReduce works great. Cool. So exactly what are the mechanics of this? So our strategy is going to be, we're going to take these z-scores that we're computing for each of these workloads, and we can just aggregate across all of them, right? We can then look for the fraction of z-scores that are greater than 2, right? So now this is a standard normal distribution. There's an expectation, because again, this is following a standard normal distribution. There's going to be expectation that some of these workloads are going to be slow, right? Just randomly things happen, right? Back-end restarts, bad network connection, who knows? But, on average, about 2% of the stuff should have z-scores greater than 2. And what we're going to do is we're just going to monitor that and make sure that that is true, that continues to be true over time. So, like I said, we expect about 2 or 5% of this workloads to have z-scores greater than 2. And when we see that fraction jump up by, a factor of 5 or a factor of 2, like 10%, right? Then that's when you should be worried, right? So what we're really measuring is that the shift in this long tail has changed, right? So essentially, if you think about it as two different distributions, the one of your baseline and the one of your new observations that you're coming in, when this long tail, when the fraction of events in this long tail increases, that means that your two distributions have now shifted, right? And so the TLDR of all this is detection. The detection mechanism that we're building is based on the fraction of these workloads exhibiting regressions in this very, very end tail, this 2 sigma tail. Okay, so let's kind of think through pictorially how this works, right? So we're going to start with all of the data, right? We're going to split it by intent to create streams of data for each intent, for each cohort. We can then take those streams of data over some historical period, say 30 days. We're going to compress them into baseline distributions and then fit them with normal distributions. Sometimes that works really well, like the yellow one. Sometimes it doesn't work so great, like the green one. Sometimes you get bimodal stuff, like the red one. But overall, this seems to work pretty well. And then we can take the stats that we get from those distributions, and we're going to put them in some database so that we have a sense of like, how well are these distributions fitting? What is our coverage? Things like that. So now for new data coming in, right? We'll get a data point in our space. This one here corresponds to the green intent. So then we'll go grab the green baseline. We'll assume it's a normal distribution. We'll compute the z-score. Again, that's the number of standard deviations away from the mean. And then we'll just write that out into our time series, right? And then we'll just repeat this for every single point that we're observing, every event that we're observing, right? And so that's what this will look like. So we'll get this time series of effectively z-scores, and then we can look at the fraction of those z-scores that are greater than 2 to look for that shift in the long tail. So at this point, we usually have quite a few questions. I'll try to head them off by answering the FAQs here. So the first one is, do the performance metrics actually follow normal distributions? Like I said before, the answer is no. Turns out that log normals actually work significantly better. And log normals, this whole process will also work with log normals. There's no reason, though, that you have to use a parameterized distribution. You could use an empirical distribution if you wanted to. The same process works. Or any other parameterized distribution. So the second question is, how do you know that these approximations hold? So for instance, like, how do you know that the normal distributions are fitting the data particularly well? Well, there's a bunch of different tests that you can do. For instance, we do KS tests, KS-stat tests to make sure that the distributions are approximately correct. And then we keep the distributions, or we keep the cohorts that fit well. And the ones that don't fit well, like the bimodal ones or the ones with really wide variances, we'll just drop those ones for now. Okay, so the next question is, how do you define these cohorts? Well, there's lots of different ways to combine cohorts. You could use complicated clustering algorithms. That's where we started. Turns out that you don't have to do something complicated. You could do something really simple. And so what we found is doing things like even taking the cross product of a small number of features, say 3 to 5, works really well. It tends to cluster workloads that have similar intents. It's not a guarantee that it's going to work. There is a little bit of trial and error in here, but in general, it works pretty well. All right, so how do we deal with these singletons or infrequent workloads? Well, the thing about singletons is that they're workloads that we haven't seen before, right? So by definition, they're workloads that, in general, it's not really clear how long they should take. And so we don't really worry about these ones. This technique doesn't work particularly well. It's not meant to detect regression shifts in singletons. We're really focusing on these kind of repeated workloads. Aren't there a lot of these singleton workloads? Well, again, it depends on what the cohorts look like. If you're getting too many singleton workloads, that's probably an indication that you're not picking the right set of features to create your cohorts at the beginning. That said, depending on what your use case is, you can have coverage that's, we've got some of the implementations that we're looking at that have coverages of only about 10 or 15% of the workloads, and the rest are singletons. And they actually are being able to detect real incidents in production. So while we like to have the coverage much higher, it's not necessary depending, again, on exactly what your use case is.
Well, and practically speaking, we've had teams that get great results with 3 to 4% coverage.
Yeah.
Even, right? Of course, the higher the coverage, the better, but you get really meaningful signals even at very, very low coverage rates.
Yeah. So everything I've explained right now feels pretty simple. Normal distribution, z-scores. I think the obvious question that everyone should have is like, yeah, but like, does this actually work? And so let me give you some example from one of the services that we've implemented this on internally. And you can see that the failure in the probes at the top correlates almost exactly with the fraction of z-scores below. And what the on-caller found that was really kind of validating to us was that they really liked how well these two graphs lined up, considering the fact that they had to do exactly 0 tuning for the bottom graph and had to do a ton of tuning for the top one. Another service that's implemented this more forward-looking has noticed that in the 9 months that they've been running this on production data, they've only found one false positive. Everything else that we found was actually, like, even if they weren't able to see it in their current monitoring, once they started digging into it, they realized that it actually was a real underlying issue.
I think there's a larger point to make about back testing, right? If someone showed up and they said, hey, I can tell you when your system is broken, I don't need to tune it, I don't need to know anything about your service, I'd probably call bullshit on that, right? Like, this is a pretty big, this is a tall order, right?
Yep.
And so every time that we implement this for a service, we go through a really extensive backtesting process, looking at previous incidents, looking at real data from the service, running it for some period of time. And so far, it appears to work on all of the services that we have run it against, right? So we really think that even with all the caveats, so for example, Brent mentioned the normal distribution thing. We all know that normals don't approximate actual performance. Even with that simplification, this works. And so we think that this is really actually hitting some core properties of distributed systems that are important.
And the other thing that's really interesting is that when we implement this for the first time on any service, what we find is we actually do detect things. And it's typically we find stuff that they haven't ever seen before, but once we look into it, there actually is something there. So we're uncovering things that have been lurking in the background systems for quite some time undetected.
Yeah, roughly this is just a much higher sensitivity approach.
Cool. So now we'll talk about how we can use these ideas.
OK, so we've thrown a lot of statistics at you, and we've made some pretty grand promises. But here's some real data. So this is data from a real service. This is the time series that Brent mentioned earlier. What this graph represents is the ratio of 2 sigma outliers. Right? Now the reason that we chose 2 sigma, so in say high energy physics experiments, they choose typically 3 or 5 sigma. Right? These are very, very unlikely events. We chose 2 sigma because we wanted more sensitivity than that. We don't just care about monitoring that can tell us when the system is unambiguously broken. We actually care about when the system is starting to get worse. Right? And so you see something that corresponds to all of our intuition. Right? We've all had these incidents where probers start firing and they stop firing and they start firing and they stop firing. But what's actually happening is there is a phenomena that's happening in the service. Things are starting to get worse and worse. It's a little bad at start, then it gets worse, then it gets a little better. It's sort of bouncing around. And then something falls over and it gets way, way worse. Right? So the sensitivity is really interesting here. The first question that we always get is, can we do this with real-time alerting? Right? Because you want to know the moment it changes. But the thing that's really fascinating is that the distance between those 2 lines is 18 hours. Right? So the reason that I mention that we use 2 sigma as opposed to 3 or 5 is because this gives us more sensitivity to these events that are probably issues but aren't definitely issues. Right? And if you see enough of these things that are probably issues, you have a problem. Right? Like either you're really unlucky, like really, really unlucky, or the system is actually kind of hosed and you should do something about it. Right? And so what we see is we actually see curves that approximate our experience with outages. They start and they're low grade at first, and they get, maybe they actually persist over, in some case, days or weeks. Right? We see some issues that start off very, very slow burn. Things are getting worse bit by bit, and you can see that things are consistently getting worse, right? But they don't get bad enough that the services start to have problems until later, right? And if you think about why this is, many of our services, like if you go back to the error recognition question, how do we recognize errors in distributed systems usually? Well, deadlines, right? There's 2 ways that services manifest errors. It's either validation failures, where situation cannot happen, throw error, or you tried to do something, your deadline was exceeded, and you're like, OK, this didn't work. I'm throwing an error instead. Right? So if you think about what's happening here, at some point you'll hit that deadline that will cascade over into errors. But until that happens, the system continues to function, albeit in a degraded form. Right? So if you think about what this is showing, this is actually showing a more sensitive version of errors, at least deadline errors. And this means that you can see problems as they start to happen, as opposed to once they've knocked the whole system over. And the fact that you can see these so much further in advance is huge, right? Like, who loves being paged at 3 a.m.? Anybody? No. So it's much better if when you get up in the morning, you can drink your morning coffee and look at the issues that the system has starting to bubble up, as opposed to the systems that the issue that has caught fire so much that you need to page someone and have them respond within 10 minutes, whether they're awake or not. Right? And I think that this really opens up a lot of really tantalizing possibilities for proactive engagement. Like, we need proactive interventions for our services. That's what I think maturity starts to look like here. So this is a great demonstration. We have at this point hundreds of these that we could show, but many of them follow this form. In some cases, they're much more abrupt than this. So imagine you push out a new version of software and you don't canary for some reason, right? You would see, very abrupt changes. There are other cases that can cause abrupt changes, but there's a world of these slow burn kinds of outages that don't just happen. It's not that you pushed a new broken piece of code to prod. It's that the system was getting overloaded, and then it was getting more overloaded, and then eventually it just couldn't keep up anymore and it fell over, right? And these are the kinds of things that we need to be able to see if we want to be able to fix these problems before they happen.
Or the environment that the service was working in is changing over time.
Sure, yeah. We've also seen cases where the service is fine and it hasn't been changed, and we change the resource mix in the pool of resources that the service is running in. And you can tell exactly when new users are added, because that's when the performance changes, right? And so this also gives you the change points in this give you a set of times that you should pay attention to, which helps in diagnosis. Okay, so the next thing that we can do with this is diagnosis. So, the first question that you get is it working? And then the second question is, can you make it work, right? How do you make the problem stop? And this is, of course, very complicated, and I won't claim that we have a general purpose solution to all instances of this problem, but here's the analytical approach that we've taken. So basically, you run the 2 sigma approach on a whole bunch of metrics, all in parallel. And these are all independently trained in the sense of building baselines and so forth. And then you set up a hierarchy, right? So imagine that you have some request, and you've all seen things like this. The total request time is the top level metric, and the total request time is comprised of the time it spends in the queue and the time it spends executing, and the execution time has 3 or 4 parts, and this sort of builds down until you get to all of these little leaves of implementation. So now what you want to do is, for each of these metrics, you want to run 2 sigma, and you can start at this metric at the top of the tree and work your way down. So this is a real graph from production. It's always amazing when you see square wave graphs. They're always exciting. So what this graph shows, the blue line is the percentage of 2 sigma outliers for total time. And then what we do is we subselect as you go down the tree. So when we look at the, for example, execution time or I/O time, these are the proportion of 2 sigma outliers of the parent, right? So as you work down the tree, you're sort of zooming in to where the problem is. Now, by the time we get to I/O time, you'll recognize that as a 5-day long period in which in all 2 sigma outliers for total time, 100% of those requests had a 2 sigma outlier for I/O time. So I/O was broken, like broken with a capital B.
Badly.
And this is an unambiguous signal that we were able to detect. So people didn't need to recognize this. This is just the results of the analysis. And this actually helped us considerably in working with the team that operates that service in order to get the problem fixed. Luckily, this was a service that we could drain out of that cell during that period. But these problems are complicated. They take time to fix. But it really helps a lot if you have dependencies that you can figure out which of them is problematic or not, rule things in and out. And so this ends up being a really great example of the kinds of diagnoses that you can do. Now, this isn't a silver bullet. None of this is a silver bullet. It turns out that our services also have complex feedback loops, and so there are many cases where different components of the system can cause slow performance in each other, and so you don't necessarily get a smoking gun like this case, but I mean, square waves like this, like, it's terrifying. Like, was everybody terrified when they saw this graph? Like, something bad is going on. So this is a great example. It's not always this simple. Okay, so the next thing you can do with this, you'll recognize this is the exact same issue that we were talking about. We've coined a term, excursions. So you could think of these as being sort of like incidents, but what an excursion is basically is a situation in which the service stops performing the way that you expect it to, right? And so the excursion starts when the performance goes off, and it ends when the performance returns to normal, right? I was talking earlier about how we have this lack of precision in our terminology, and there was the whole talk about how incidents are a social construct. This doesn't look like a social construct to me, for the record. This is an actual service that is in distress. And so I think that we can see these things unambiguously, but the reason that we use excursion and not incident is that there are so many other semantics that are loaded up on it, right? So for example, sometimes people say, well, you only have an incident if customers notice, or you only have an incident if there's a response, or there's a lot of different sort of process-based constraints on what does and doesn't consist of or what an incident does or doesn't consist of. And so we call these excursions. Now, one of the things that's really interesting is that if you look at the area under the curve, you can get a nice quantitative sense of how bad it is. And this allows us to actually rank these excursions, because it turns out that once you turn your sensitivity up, it's sort of like turning over a rock in the Pacific Northwest, right? You find spiders, and just more and more spiders, right? There are all of these performance events that we were unable to see before, and this is a particularly severe one. But there are plenty of excursions that'll maybe hit 20% outlier rate, and that's still a substantial degradation. So these little things that go bump in the night, we can now see, and we can actually estimate how large they are. And in particular, one of the things that we can say that's really interesting is if you think about all of the events that are under that curve, those are the actual impact of the outage, right? Who's had an outage where some chunk of the workload was impacted and the rest of the workload was fine? That tells you which chunk of the workload was affected. Right? So you can use this to work backwards and figure out what the common factors in those workloads are. You can identify the customers that are impacted. And so this is a really powerful tool for understanding what it means that you had an outage. Okay, so this is the point where I'm going to go off on one of my hobby horses for a minute. And folks that know me will recognize that I just do this sometimes. So I have this theory, and it's kind of a crazy theory, but I have this theory that that the point of distributed systems from a reliability perspective is to produce decorrelation. Right, if you think about why you put an application on a distributed system versus just like a process on a machine, you want to decorrelate between the performance and failure of components, whether they're software components or hardware components. And so if you think about distributed systems from that perspective, the whole point of them is to maintain correlation state. Right? There's lots of things that you want to remain decorrelated, and if they correlate, you're in for a bad time. Roughly, right? So to give a really concrete example, imagine that you have a service and a dependency that it consumes. So generally speaking, a dependency will be providing service to lots of consumers. And so unless the consumer is the big user of that service, they will have different stories of production, right? The traffic the traffic to the dependency from the service that you're running will just be a small fraction of the workload, and it's just one of many consumers, right? However, if a service and its dependency correlate, it is almost certainly the case that the dependency is causing an outage in the caller. Right? So if you see metrics that suggest inside of your service that you're having a problem, and you also see metrics inside of your service that describe your consumption of a dependency, and they start to correlate after they never correlated before, that's a good place to look for a problem. Right? So this measure is actually sensitive enough that we can measure when we see correlation and when we don't. And in a lot of cases, we don't want correlation most of the time, right? You know, another way to think about correlation is, you know, cloud providers, one of the things that is really critical for us to provide for our customers is isolation between regions. You don't want those two regions to correlate, right? Now, at the end of the day, it is impossible to produce regions that never ever correlate for any reason because they all exist on the planet Earth, right? But the risks of those things happening are really, really low, right? But as you start to look at larger and larger correlation risks, these are real. And this is a calibration-free mechanism that we can use to measure correlation in prod, and I think that's awesome. Okay, so here is another interesting use case. So all of the analyses that we've been looking at so far have been doing time series analysis and basically testing the hypothesis that Brent mentioned, that we're trying to see that a service is still performing the way that it used to perform. But time is just one of the dimensions that we can pivot on, right? So it turns out that you can characterize your workload based on lots of different things and look at either the absolute or relative performance of your workload based on these approximate cohorts that we've created. So say, for example, you're rolling out a new experiment. These are always characterized sort of insufficiently, right? You know, how do we do this? You're rolling out a performance optimization. Is this a net win? Because you've got a lot of different workloads. Well, you run a benchmark against 5 of your key workloads, and you come up with some sort of aggregation, and you're like, oh, it's 3% faster. OK, so this is good. We're going to do it. Right? But it turns out that your service probably, if it's a large service, has hundreds or thousands of workloads. And they're all different. And some of them are going to be affected a little bit, and some will be affected a lot. And by using these cohort-specific views, we can actually really understand, on a workload-by-workload basis, how is this change perturbing the system. So anyway, we think that the approximate cohort technique, even independent of 2 sigma, is actually a really useful thing, and we're starting to explore a lot more applications of it now. OK, so conclusions. So I think that there's a bunch of important observations that we've started out here. You know, Brent spent a bunch of time talking about how reliability is a shared property. And I think that we are almost all in the situation where we don't have enough information in our heads as either the consumer or provider of a service to be able to fully reconstruct what's going on. So we need better mechanisms to really reconstruct the end-to-end behavior, because that's actually what everyone cares about, right? Even if you can see the things in your sandbox, that's not enough no matter which side of this divide you're on. So we need better mechanisms to exchange information and to really put together the big picture. I think that the second observation that's critical is, you know, variability is what everybody cares about. So if you were to offer me a service that was 10% faster but you know, 3 times more volatile, I'll take the slower service every time, and I suspect many of you would as well, right? So this is a key metric that we need to measure in our systems and really deeply understand, because it turns out it's what everybody cares about. The third thing that I was just talking about is distributed systems often produce decorrelation. We can measure it and its absence, and I think that this is actually a really critical tool that we're going to dig into more in the future. Correlating these metrics across multiple hierarchical metrics can identify proximate causes. The other thing we didn't actually talk about very much, but ends up being really pivotal to how this approach works and why it works, is that the scored events end up being combinable, right? So if you think about, say, a latency measurement with 6 orders of magnitude of variation, you can't put those in a bucket and get anything but mush, right? But when you normalize all of these things into the same domain, you can meaningfully combine them along many different dimensions in order to answer A/B questions, in order to understand what the effect of your rollout was, in order to understand how things change over time. And this is how you gain actual statistical power over the system, which is what we need to see phenomena that are as fine-grained as our systems experience. I hope that you're convinced that error recognition is only a gestalt of human judgment over time. There is no objective reality there, and I don't think you'll ever find any objective reality. That's my opinion. I think this is an incredibly important point. There's this moment. Has anybody ever debugged an incident and found a bug in a dashboard while you're debugging the incident? Right? That feeling of lost trust that you feel is horrible, and you'll never trust the dashboard again. Right? I hope that you all start to feel this way about errors. Right? They can be indicative, but they aren't ground truth reality, and they never will be. And at the end of the day, because SLOs are built on the idea that we can decide whether or not events are good or bad, SLOs can't work. And we aren't going to be able to solve our reliability problems by analyzing our systems using SLOs. Now, luckily, we have something better that we've built here. So, as a quick review, this is a method that takes the workload, breaks it into pieces, estimates the likely performance distributions of each piece, and then is able to use those baselines to score events as they come in, which we can combine relatively arbitrarily along the time domain or other arbitrary dimensions in order to answer real concrete questions about what our systems are doing compared to what we expect them to be doing. This is useful for a large variety of applications. We have ended up with really some jaw-dropping things that we have found with this. Well, we're all sort of cynical because we're SREs, right? It's been an interesting process trying to take a complex analytical tool and put it in front of a team that's using it to try to diagnose real issues and see what the process is like that they develop trust in it. But the comment that Brent mentioned earlier was really interesting about the very, very low false positive rate. The same engineer actually told us at one point a few months ago that they had convened a war room of 10 people for 2 days only on the basis of these alerts. There had been no customer complaints yet. After a day and a half, the customer complaints started rolling in. Right? So we're pretty convinced that we have a high fidelity method that really captures what people actually care about in a system. We didn't really talk very much about the calibration-free part in Insight. The calibration-free aspect of the analysis. But I think this is really important. Calibration is just another opportunity to make a mistake. And we do this all the time, right? The best case scenario for human accuracy and repeated processes is not 100%, and it never will be, right? And the more judgment that we put in the middle of the system, the harder this ends up being. A couple of closing thoughts. We need to do better than what we've been doing with reliability analytics, but I think we can. This is a proof point. We're not saying this is the last word in this by any means. There will be other methods. We hope that there are lots of other methods. Please try to develop methods like this, because I think we will all be better off for it. The other point that I think is critical is that performance data is so much better than availability data, and it'll tell you 95% of the same things. You will find much more signal there. You will find way more insights there. And you have to deal with a whole lot less noise. Again, to echo my talk from the last SREcon, we need more models. This is one model that covers one aspect of system behavior. There are many, many more invariants that you could try to validate in the same way, and we need them, right? We all need them. And the last thing, we need help. We have openings. Talk to Brent or me if you're interested. I think we have a kind of unusual team, and we think we're doing cool stuff. Thank you very much.